Imagine grabbing a sugar cube and feeling it weigh 1 billion tons in your hand. That's the density of a neutron star, where matter gets crushed so hard that a teaspoon would outweigh Mount Everest. These objects pack more mass than our entire sun into something the size of a city, making them the densest things in the universe that we can actually see. Black holes might be denser, but we can't look inside them. With neutron stars, there's no event horizon hiding the secrets. Scientists can study them directly, and what they're finding is completely rewriting the rules of physics. If you want to see just how deep this rabbit hole goes, smash that like button and subscribe, because what's hiding in the core of these stars is way stranger than anyone predicted. The pressure inside is so extreme that normal matter doesn't exist anymore. Atoms collapse, neutrons break down, and something truly bizarre takes over. Something that might be older than the universe itself. Prepare yourselves. We begin. When you start peeling back the structure of a neutron star, you realize pretty quickly that calling it a star is almost misleading, because what you're really looking at is more like an onion made of impossibility, where each layer defies everything we know about how matter should behave under normal circumstances. The journey starts at the surface, with what scientists call the outer crust, and even here at the very beginning, things are already breaking the rules in ways that sound like science fiction. This crust is only a few hundred meters thick, which seems thin until you remember we're talking about an object that's already been crushed down to the size of a city. And within that thin shell, you've got matter arranged in a crystalline lattice, so dense and so tightly packed that it makes steel look like cotton candy in comparison. The atoms here are ionized, meaning the electrons have been stripped away and are flowing freely through the gaps between atomic nuclei that have been crushed together into the most rigid, solid structure in the entire universe. This isn't just harder than diamond or tungsten or any exotic material we can manufacture in a laboratory. This is orders of magnitude stronger, and the reason comes down to pure gravitational compression, forcing every atom to sit shoulder to shoulder with its neighbors, under pressures that would instantly vaporize anything we could bring from Earth. The nuclei in this outer crust are likely iron at first, because iron has one of the highest binding energies per nucleon, meaning it's one of the most stable configurations of protons and neutrons you can get. But as you descend deeper and the pressure climbs higher, something fascinating starts to happen. The nuclei become more and more neutron-rich, because at these densities, it becomes energetically favorable for protons to capture electrons and transform into neutrons through a process called inverse beta decay. So the deeper you go, the more the matter shifts away from anything resembling the periodic table we learned in school and starts becoming something alien. At around 10 to the power of 7 grams per cubic centimeter, you're already in territory where the composition of nuclei is nothing like what you'd find anywhere else in the universe, except maybe in the heart of a supernova explosion. And this is just the beginning of the strangeness, because beneath the outer crust lies a boundary that scientists call the neutron drip point, and this is where things take a sharp turn into the truly bizarre. At approximately 4 times 10 to the power of 11 grams per cubic centimeter, the density reaches a threshold where neutrons can no longer stay bound inside atomic nuclei, and they start to drip out like water, seeping through cracks in a dam, flooding the spaces between the nuclei and turning the inner crust into something that's part solid and part liquid, a hybrid state of matter that we have absolutely no way of reproducing in any laboratory on Earth. The neutrons that drip out don't just sit there doing nothing either. They form what's called a neutron superfluid, which is a state of matter where the particles flow without any friction or resistance whatsoever, meaning if you could somehow stir this neutron fluid, it would keep spinning forever without slowing down, because there's nothing to dissipate the energy. This isn't theoretical speculation. We actually have observational evidence that this is happening because of something called pulsar glitches, which are sudden jumps in the rotation speed of spinning neutron stars that happen when the superfluid interior and the solid crust fall out of sync and then suddenly snap back into alignment, releasing angular momentum in a burst that we can detect from Earth. The Vela pulsar, one of the most studied objects in the sky, shows these glitches repeatedly, and each one gives scientists another clue about how the superfluid layers deep inside are interacting with the crust above them. The inner crust itself becomes increasingly strange as you go deeper because the nuclei start to deform under the relentless pressure, and instead of maintaining their roughly spherical shape, they begin to stretch and merge into bizarre configurations that physicists have nicknamed nuclear pasta because of how they look in computer simulations. At relatively lower densities within the inner crust, you get what's called the Noki phase, where nuclei are still somewhat spherical but clustered together like dumplings. And as the density increases, these spheres elongate into rod-like structures that resemble spaghetti. Then, at even higher densities, the rods flatten and merge into sheets that look like lasagna. And if you go deeper still, the structure inverts, and you get the antipasta phases, where instead of matter forming shapes, you have bubbles of empty space surrounded by nuclear matter, creating Swiss cheese-like structures with holes instead of solids. These pasta phases aren't just a fun analogy. They have real physical consequences because they affect how rigid the crust is and how it responds to stress, which in turn influences everything from how the star vibrates to how it generates its magnetic field. And understanding these exotic structures is crucial for making sense of the signals we receive from neutron stars across the galaxy. But the inner crust is just a transition zone, a preview of the truly extreme conditions that await in the core. And when you finally cross the boundary into the outer core, at densities around 10 to the power of 14 grams per cubic centimeter, you enter a realm where neutrons utterly dominate the composition, making up something like 90 to 95% of all the particles present, with only a small fraction of protons and electrons mixed in to maintain charge neutrality. Here, the neutrons aren't just forming a superfluid, they're existing in a degenerate state where quantum mechanics takes over completely, and the particles are packed so tightly that their quantum wave functions overlap, creating a collective behavior that's governed by principles that have no analog in everyday experience. The protons in the outer core are thought to form a superconductor, which is similar to a superfluid, but for charged particles, meaning they can carry electrical currents with absolutely zero resistance. And this superconducting state is believed to be the engine behind some of the most powerful magnetic fields in the universe. When you hear about magnetars, which are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, strong enough to rip apart atoms from thousands of kilometers away and scramble the quantum structure of empty space itself, you're looking at the result of superconducting currents flowing through the outer core and generating magnetic flux that gets trapped and amplified as the star spins and evolves. The difference between a normal neutron star with a relatively weak magnetic field and a magnetar with a reality warping field may come down entirely to how the superconducting protons organize themselves in the outer core, whether the currents form stable loops or chaotic vortices. And this is one of the big unsolved questions in neutron star physics, because we still don't fully understand the connection between the microscopic quantum behavior of superconducting protons and the macroscopic magnetic personality that the star displays to the outside universe. The outer core is also where much of the star's mass is concentrated, making it the gravitational heart of the object. And the way matter behaves here determines how the star cools over time, because heat transport in a superfluid is completely different from heat transport in normal matter. Neutrons in a superfluid state can pair up into what are called Cooper pairs, similar to how electrons pair up in superconductors. And when this happens, the energy required to break the pairs creates what's called a pairing gap, which affects how efficiently neutrinos can be emitted from the core. And neutrinos are the primary way that neutron stars lose heat in their first few thousand years of life, because photons can only carry away heat from the surface, while neutrinos can escape directly from the core, carrying energy out at nearly the speed of light. Observations of young neutron stars like the one in the Cassiopeia, a supernova remnant, which showed a surprisingly rapid drop in surface temperature over just a decade, have provided some of the strongest evidence that the cores really are filled with superfluid neutrons, because the cooling rate matches theoretical predictions for a star undergoing a phase transition where neutrons suddenly pair up and enter the superfluid state, releasing a pulse of neutrinos in the process. This kind of observational confirmation is rare and precious in astrophysics because it gives us a direct window into processes happening deep inside an object that we can never visit or probe directly. And it shows that the bizarre quantum states we've been theorizing about aren't just mathematical curiosities, but actual physical realities that govern the behavior of these extreme objects. As you push even deeper into the neutron star, past the outer core and into the inner core, you cross another threshold where the density climbs to several times that of nuclear saturation density, which is the density at which neutrons in ordinary atomic nuclei start to touch each other. And beyond this point, we enter the realm of true uncertainty, because no experiment on Earth can recreate these conditions for more than a fraction of a second, and no theory can make predictions with complete confidence. The inner core is where the fundamental nature of matter itself becomes an open question, where the neutrons that have dominated everything up to this point might no longer be able to hold themselves together as coherent particles. At these densities, which can reach 8 or even 10 times nuclear saturation density in the most massive neutron stars, the pressure is so intense that the strong nuclear force binding quarks together inside neutrons starts to compete with the degeneracy pressure trying to keep the particles separate. And when these two fundamental forces reach an equilibrium, something extraordinary might happen. One possibility is the emergence of hyperons, which are exotic cousins of protons and neutrons that contain strange quarks instead of just the up and down quarks found in ordinary matter. And strange quarks are heavier and less stable than their lighter counterparts. But at extreme densities, they can become energetically favorable, popping into existence and mixing with the neutron-rich soup to create a zoo of particles that includes lambda hyperons, sigma hyperons, and cascade hyperons, each with different masses and different interactions with the surrounding matter. If hyperons do form in large numbers, they fundamentally change the equation of state of the core, which is the relationship between pressure and density that determines how compressible the matter is and how much mass the star can support before collapsing into a black hole. And this creates what's known as the Hyperon Puzzle, because theoretical models predict that hyperons should soften the equation of state, making the matter easier to compress and lowering the maximum possible mass of a neutron star. But observations have confirmed the existence of neutron stars, with masses exceeding 2 times the mass of our Sun, like Pulsar J0740 plus 6620, which weighs in at about 2.14 solar masses. And these massive stars shouldn't be able to exist if hyperons are present in the way standard models predict. So either the models are missing something important about how hyperons interact with each other and with neutrons, or there's another physical process at work that we haven't accounted for yet. Another possibility is the formation of meson condensates, which are collective quantum states where particles called mesons, which are made of a quark and an antiquark bound together, suddenly appear in large numbers and form a kind of quantum carpet throughout the core, changing the effective interactions between neutrons and altering how the star responds to pressure. Pions and kaons are the most commonly proposed mesons for this scenario, and if they condense into a coherent state, they could affect the cooling rate of the star, because the presence of mesons changes the energy spectrum of the core and shifts how neutrinos are produced and emitted. So scientists are looking for subtle differences in the cooling curves of neutron stars that might reveal the signature of meson condensation. But so far, the evidence is indirect and inconclusive, because there are multiple physical processes that can produce similar cooling behaviors, and disentangling them requires more precise observations than we currently have. The most radical scenario for the inner core is the breakdown of neutrons altogether. The idea that at sufficiently extreme densities, the quarks inside, protons and neutrons, become deconfined, breaking free from their individual particles and merging into a single continuous fluid of quarks and gluons that fills the core like a primordial soup. And this state of matter is called quark matter, or sometimes quark-gluon plasma. And it's the same state that scientists believe filled the entire universe in the first few microseconds after the Big Bang, when temperatures and densities were unimaginably high. If quark matter exists in the cores of neutron stars, then these objects aren't just laboratories for studying extreme physics. They're literal time capsules containing a remnant of the conditions that gave birth to everything we see around us, frozen in place by gravity and pressure, and waiting for us to figure out how to decode the signals they're sending. Some models go even further and propose that the quark matter in neutron star cores might be made up of 3 different types of quarks: up quarks, down quarks, and strange quarks, in roughly equal proportions, creating what's called strange quark matter. And the truly wild thing about strange quark matter is that some theoretical calculations suggest it might actually be more stable than ordinary nuclear matter, meaning that if you could somehow create a chunk of strange quark matter and bring it to Earth, it wouldn't decay or explode. It would just sit there being the most stable form of matter in the universe. And if this is true, then entire stars made purely of strange quark matter might exist. Objects that look like neutron stars from the outside, but are actually strange stars with no neutrons at all. Just quarks all the way through, although no confirmed strange stars have been detected yet. And the idea remains one of the most speculative possibilities in the field. The challenge with all these scenarios, whether it's hyperons or meson condensates or quark matter, is that they leave behind signatures that are incredibly subtle and hard to distinguish from one another with the tools we currently have, because the differences show up in properties like the tidal deformability of the star, which is how much the star gets stretched and squished when it's in a binary system, spiraling toward a merger, or in the exact cooling rate, which depends on the types of particles present and how they interact, or in the maximum mass, which is determined by how stiff or soft the core is under pressure. Gravitational wave detections, like the famous event GW170817, where 2 neutron stars collided and merged in a spectacular explosion, visible across the electromagnetic spectrum, have started to provide the kind of data we need to narrow down these possibilities, because the gravitational wave signal encodes information about how the stars deformed in the final moments before merger. And by analyzing that signal, scientists can place constraints on the equation of state and rule out models that predict cores that are too soft or too stiff. But even with this breakthrough, we've only observed a handful of neutron star mergers, and we need dozens or hundreds more before we can make definitive statements about what's really happening in the core. The layers of a neutron star, from the crystalline outer crust to the superfluid inner crust to the superconducting outer core to the mysterious inner core, aren't just interesting for their own sake. They're connected in intricate ways that determine everything we observe about these objects, from millions of light years away, and each layer leaves its fingerprint on the star's behavior. The rigidity of the crust influences how pulsars glitch and how starquakes propagate through the surface, creating sudden changes in the rotation period that we can time with millisecond precision using radio telescopes. And those glitches in turn tell us about the coupling between the solid crust and the superfluid layers below, giving us a way to probe the interior without ever seeing it directly. The superfluid and superconducting properties of the outer core determine how the star cools over its first 100,000 years of life. As neutrinos flood out from the core, carrying away thermal energy and leaving behind a gradually darkening ember that will take billions of years to fully fade. And by measuring the surface temperature of neutron stars of different ages, we can trace the cooling curve and compare it to theoretical models that make predictions based on different assumptions about what particles are present in the core and how they're behaving. The inner core, despite being the most uncertain part of the structure, is in many ways the most important because it sets the ultimate limit on how massive a neutron star can be before the pressure becomes too great and the entire object collapses inward, past the point of no return, crossing the event horizon and becoming a black hole. And finding that maximum mass limit is one of the holy grails of neutron star research, because it will tell us which models of exotic matter are correct and which ones need to be thrown out. The fact that we've already found neutron stars with masses over 2 solar masses, like PSR J0348 plus 0432, which clocks in at around 2.01 solar masses, and PSR J0740 plus 620, which is even heavier, tells us that the core has to be stiff enough to support that much mass without collapsing, which immediately rules out some of the softer equations of state that predict exotic matter would make the core too compressible. But there's still a huge range of models that remain consistent with the observations, and the only way to narrow that range further is to keep searching for even more massive neutron stars, or to get more precise measurements of the radius, because the mass alone isn't enough to fully constrain the equation of state. You need both mass and radius together to pin down the relationship between pressure and density. NASA's NICER telescope, which is mounted on the International Space Station and measures X-rays from the surfaces of pulsars with incredible precision, has been a game changer in this regard because it can measure the size of neutron stars by looking at how the X-ray emission varies as the star rotates. And from that variation, scientists can infer both the radius and the mass with enough accuracy to start distinguishing between competing models of the core. And early results from NICER observations of pulsars like PSR J0030 plus 0451 have already started to narrow the range of possible equations of state, showing that the cores are neither extremely soft nor impossibly rigid, but somewhere in between, which is valuable information, even if it doesn't give us a final answer yet. The layers of strangeness inside a neutron star are more than just a curiosity. They're a roadmap to understanding how matter behaves when it's pushed to the absolute edge of what the universe allows. And every observation we make, every gravitational wave we detect, every pulsar glitch we time, every cooling curve we measure, adds another piece to the puzzle and brings us closer to answering one of the most fundamental questions in physics, which is what happens to matter when you compress it beyond the breaking point of atoms, beyond the limits of nuclei, beyond anything we can test in a laboratory. And the answer to that question is hidden inside the cores of neutron stars, waiting in the layers of exotic matter that exist nowhere else in the cosmos, protected by gravity, and revealed only through the faint signals that reach us across the void of space. The inner core of a neutron star represents something that shouldn't exist, according to everything we understand about everyday matter. A place where the rules we've spent centuries establishing through careful experiments and observations simply stop applying, and new physics takes over. Physics that we can barely glimpse through our most advanced theories, and that pushes the boundaries of what we can predict with any real confidence. This region begins at a depth where the density crosses roughly 2 to 3 times nuclear saturation density, which is the point at which the nuclei in ordinary atoms are packed as tightly as they can go before they start touching each other. And once you exceed that threshold, you're no longer dealing with neutrons as discrete particles with well-defined boundaries, but rather with a fluid where the distinction between one neutron and another starts to blur, and the collective behavior of billions upon billions of particles governed by quantum mechanics becomes the only thing that matters. The pressure in the forbidden zone is so extreme that it defies comparison to anything we encounter in normal life, or even in most extreme astrophysical environments. We're talking about pressures that exceed 10 to the power of 34 dynes per square centimeter, which is a number so large that it loses all meaning when you try to visualize it. But to give you some context, this is millions of times greater than the pressure at the center of the sun, and billions of times greater than anything we could create in a laboratory, even with our most powerful particle accelerators, smashing nuclei together at nearly the speed of light. At these densities, which can reach 8, 10, or even 12 times nuclear saturation density, in the most massive neutron stars, the neutrons themselves are being squeezed so hard that their internal structure, the arrangement of quarks and gluons that normally holds them together as stable particles, starts to feel the strain. And this is where the question becomes not just what phase of matter exists, but whether neutrons can even survive as coherent objects, or if they break apart into something more fundamental. The Forbidden Zone earned its name, not because it's literally impossible to study, but because it represents a frontier where our experimental tools fail us completely, where the physics we've confirmed in laboratories reaches its limit, and we have to rely entirely on theoretical models that extrapolate far beyond anything we can directly test. And those models, while sophisticated and grounded in our best understanding of quantum chromodynamics and the strong nuclear force, still leave enormous room for uncertainty, because the equations governing quark interactions become so mathematically complex at these densities that we can't solve them exactly, and have to make approximations that may or may not capture the true behavior of matter under these conditions. One of the primary candidates for what exists in the Forbidden Zone is hyperons, which are particles that look superficially similar to protons and neutrons, but contain at least one strange quark, instead of only up and down quarks. And strange quarks are one step heavier and less stable than the quarks found in ordinary matter. But at extreme densities, the energy cost of creating them can be offset by the energy gained from having more types of particles available to fill different quantum states, which helps manage the degeneracy pressure that's trying to blow the star apart. The hyperons that physicists expect to find include lambda particles, which have an up quark, a down quark, and a strange quark, sigma particles, which come in positive, neutral, and negative varieties, depending on their charge distribution, and cascade particles, which contain two strange quarks and can be even more exotic. And if these particles form in significant numbers, they fundamentally alter the equation of state, because they provide additional channels for the system to relieve pressure, making the core softer and more compressible, which sounds harmless until you realize that a softer core means the star can support less mass before collapsing into a black hole. And this creates the Hyperon Puzzle that has plagued neutron star physics for decades. The puzzle arises because early theoretical models predicted that hyperons should appear at densities around 2 to 3 times nuclear saturation density, which is definitely reached in the cores of even moderately massive neutron stars. And once hyperons form in large numbers, they soften the equation of state so much that the maximum possible mass for a neutron star drops to somewhere around 1.5 solar masses. But this prediction was completely shattered when astronomers started discovering neutron stars that weigh more than 2 solar masses, like Pulsar J 0740 plus 6620, which has been measured at approximately 2.14 solar masses, with a margin of error so small that there's no doubt it's heavier than 2 suns. And the existence of these massive stars tells us unequivocally that something is wrong with the simple hyperon models. Because if hyperons were forming the way we thought they should, these stars would have already collapsed into black holes, so either hyperons don't form as readily as predicted, or there's some additional repulsive interaction between hyperons and neutrons that we haven't accounted for that stiffens the equation of state and allows the core to support more mass. And figuring out which of these explanations is correct is one of the most active areas of research in nuclear astrophysics right now. Another possibility for the forbidden zone is the formation of meson condensates, which are collective quantum states, where mesons, particles made of a quark bound to an antiquark, suddenly appear in large numbers throughout the core and organize themselves into a coherent quantum field that permeates the entire region. And the most commonly discussed candidates are pion condensates, because these mesons have the right properties to become energetically favorable at high densities. Pions are the lightest mesons, made of up and down quarks, paired with their antiparticles, and they play a crucial role in mediating the strong nuclear force between nucleons. So it's not unreasonable to think that at extreme densities, they might condense out of the quantum vacuum and form a stable background field that changes how neutrons interact with each other. And if pion condensation occurs, it could soften the equation of state in a similar way to hyperons, making the star more compressible and lowering the maximum mass. But the predictions for exactly when and how pion condensation happens are highly sensitive to the details of the nuclear force and the specific density and temperature conditions in the core. So there's still a lot of uncertainty about whether this is actually happening in real neutron stars. Kaons are heavier mesons that contain strange quarks, and kaon condensation is particularly interesting because it involves the production of strangeness in the core, which is another way the system can access new quantum states and relieve pressure. And some models suggest that kaon condensation could occur at densities slightly below where hyperons would form, creating a phase transition that changes the properties of the core before the Hyperon puzzle even becomes an issue. But again, the observational evidence for kaon condensates is indirect at best and relies on looking for subtle signatures in the cooling behavior or the mass-radius relationship of neutron stars that could just as easily be explained by other physical processes. The most radical and most fascinating possibility for what lurks in the forbidden zone is quark matter. The idea that at sufficiently high densities, the neutrons completely break down and their constituent quarks become deconfined, no longer bound within individual particles, but free to move throughout the core as a single continuous fluid of up quarks, down quarks, and gluons, the fundamental particles that mediate the strong force. And this state of matter is called quark-gluon plasma, and it's the same phase that scientists believe filled the entire universe in the first few microseconds after the Big Bang, when temperatures were in the trillions of degrees and densities were unimaginably high. So if quark matter exists in neutron star cores, then these objects aren't just interesting astrophysical phenomena, they're actual physical laboratories, preserving a remnant of the conditions that gave birth to everything we see in the cosmos today. Frozen in time and space by the crushing grip of gravity, the transition from neutron matter to quark matter would be a genuine phase transition, like water freezing into ice or boiling into steam. Except, instead of molecules rearranging themselves, you have fundamental particles reorganizing from one state of confinement to another, and this transition could happen abruptly at a specific critical density where the pressure suddenly jumps and the structure of the core fundamentally changes. Or it could happen gradually over a range of densities with a mixed phase where blobs of quark matter coexist with regions of neutron matter in a kind of cosmic emulsion, and distinguishing between these scenarios is incredibly difficult because the signatures they leave are subtle and require precise measurements of properties like tidal deformability and cooling rates that we're only just beginning to be able to measure with instruments like the NICER telescope and gravitational wave detectors. Some theoretical models go even further and propose that the quark matter in neutron star cores isn't just made of up and down quarks, but also contains a significant population of strange quarks, creating what's called strange quark matter. And the truly wild implication of strange quark matter is that it might actually be more stable than ordinary nuclear matter, meaning that if you could somehow extract a chunk of it from the core and bring it to Earth, it wouldn't decay or explode, but would simply remain stable indefinitely because it's in a lower energy state than protons and neutrons. And if this hypothesis is true, then it opens up the possibility of strange stars, objects that look like neutron stars from the outside, but are actually made entirely of strange quark matter from their surface all the way down to their center, with no crust and no neutron-rich layers, just quarks all the way through. And while no confirmed strange stars have been identified, yet there are a handful of neutron star candidates with properties that don't quite fit the standard models, and that could potentially be explained if they're actually strange stars masquerading as ordinary neutron stars. The challenge with identifying what's really in the forbidden zone is that all these different scenarios, hyperons, meson condensates, quark matter, strange quark matter, produce effects that are maddeningly similar when viewed from the outside, because we can't drill into a neutron star or send a probe to measure the composition directly. We have to infer what's inside based on macroscopic properties like the star's mass, its radius, how it cools over time, how it responds to tidal forces during a merger, and how its rotation changes when it glitches. And each of these observables is influenced by the equation of state in a slightly different way, but the differences are often small enough that they fall within the margin of error of our measurements, which means multiple competing models can remain consistent with the data even as we gather more and more observation. Gravitational wave astronomy has been a breakthrough in this regard, because when two neutron stars spiral into each other and merge, they produce ripples in space-time that encode information about how the stars deform under the extreme tidal forces they experience in the final moments before collision. And this tidal deformability is directly related to how stiff or soft the core is, with a softer core producing a larger deformation and a stronger tidal signature in the gravitational wave signal. And the famous event, GW170817, which was the first neutron star merger detected by LIGO and Virgo in August 2017, provided the first direct measurement of tidal deformability and immediately ruled out some of the softest equations of state that predicted cores dominated by hyperons or exotic matter that would make the stars too squishy. But even with this landmark detection, we only have one high-quality measurement, and we need dozens of additional mergers observed with similar precision before we can really start to distinguish between the remaining models with confidence. The cooling behavior of neutron stars also provides clues about the forbidden zone, because the rate at which a star loses heat depends critically on what particles are present in the core and how they interact, with different types of matter producing different cooling curves that can potentially be distinguished if we have enough data. And the key process is neutrino emission, because neutrinos can escape directly from the core carrying away energy, unlike photons, which can only radiate from the surface. So the core composition determines how efficiently neutrinos are produced and how quickly the star cools. And observations of young neutron stars like the one in the Cassiopeia, a supernova remnant, which showed a surprisingly rapid temperature drop over just 10 years, have provided some of the strongest evidence that the cores really do contain exotic matter in superfluid states that enhance neutrino emission through processes like the breaking and reforming of neutron-Cooper pairs. But again, the interpretation of these cooling observations is complicated by the many uncertain factors involved, including the exact temperature and density profile of the core, the thickness and composition of the crust, which acts as an insulating blanket, and the strength and structure of the magnetic field, which can affect heat transport. So while the data is suggestive, it's not yet definitive. The maximum mass of a neutron star is perhaps the single most important constraint on what exists in the forbidden zone, because it's directly determined by the equation of state, with a stiffer core able to support more mass before the pressure becomes insufficient to resist gravitational collapse. And the star crosses the threshold to become a black hole, and the current record holders are pulsars like J0740 plus 6620 and J0348 plus 0432, which both exceed 2 solar masses and possibly approach 2.2 or even higher, depending on the precise measurements. And every time a new record is set, it forces theorists to go back and revise their models, because any equation of state that predicts a maximum mass below the observed value is immediately ruled out. And this process of elimination has been incredibly valuable in narrowing down the possibilities, even if it hasn't yet given us a definitive answer about what's really in the core. Some researchers have proposed hybrid star models where the core has a layered structure with normal neutron matter in the outer regions, transitioning to quark matter in the very center, creating a core within a core. And these hybrid models can potentially reconcile the existence of heavy neutron stars with the presence of exotic matter, because the quark core only forms at the very highest densities in the most massive stars, while lighter stars remain purely hadronic with no quark matter present. And the phase transition between hadronic and quark matter could leave observable signatures in the mass-radius relationship, creating a kink or discontinuity in the curve that might be detectable with future observations from instruments like NICER, which can measure both mass and radius simultaneously for multiple pulsars. But so far, the data quality isn't good enough to confirm or rule out these hybrid scenarios. The forbidden zone also raises fundamental questions about the nature of the strong nuclear force itself, because the force between quarks is mediated by gluons and is described by quantum chromodynamics, which is one of the pillars of the standard model of particle physics. But QCD is notoriously difficult to work with at the densities relevant to neutron star cores, because the force becomes strongly coupled, meaning the interactions are so intense that the usual perturbative methods we use to calculate things in particle physics break down completely, and we have to resort to alternative techniques like lattice QCD, which involves discretizing spacetime and solving the equations numerically on supercomputers. But even lattice QCD has limitations because it's computationally expensive and struggles with certain regimes of density and temperature. So there are still large swaths of the QCD phase diagram that remain poorly explored, and neutron stars are one of the few places in the universe where nature has done the experiment for us by creating these conditions and holding them stable for millions of years. The uncertainty about what exists in the forbidden zone isn't a sign that physics has failed or that we're missing some fundamental principle. It's more a reflection of just how extreme these conditions are and how far we're pushing our theories beyond the regimes where they've been directly tested. Because the density in the forbidden zone is higher than anything we can create in particle accelerators, and the particles are packed together so tightly that quantum effects dominate on scales that range from individual quarks all the way up to the entire star, creating a complex interplay between microscopic physics and macroscopic structure that we're only beginning to understand. And every new observation, whether it's a gravitational wave detection, a precise mass measurement, a radius constraint from NICER, or a cooling curve from a young supernova remnant, adds another piece to the puzzle and helps us narrow down the possibilities, even if we haven't yet arrived at a complete picture. The forbidden zone matters not just because it's a curiosity, or because we want to understand neutron stars for their own sake, but because it connects to some of the deepest questions in physics about the nature of matter, the behavior of the strong force, and the conditions that existed in the early universe. And if we can definitively prove that quark matter exists in neutron star cores, it would be one of the most significant discoveries in modern physics, confirming that we can access the primordial state of the cosmos, not by building ever larger particle accelerators, but by studying the remnants of stellar explosions across the galaxy. And conversely, if we find that neutron star cores are made purely of hadronic matter with no exotic particles, then that would also be a major discovery, because it would mean that nuclear matter is far more resilient than we thought, and can withstand pressures that exceed our wildest predictions without breaking down into more fundamental constituents. And either outcome would reshape our understanding of how matter behaves when pushed to the absolute edge of what the universe allows. The Forbidden Zone remains one of the last great mysteries in astrophysics, precisely because it exists at the intersection of so many different fields: nuclear physics, particle physics, quantum mechanics, general relativity, and observational astronomy. And solving the mystery requires advances in all these areas simultaneously, from better theoretical models of QCD at high density to more sensitive gravitational wave detectors, to more precise measurements of neutron star masses and radii. And the progress being made is remarkable, even if the final answer remains elusive, because with each passing year, we're getting closer to understanding what happens when you take ordinary matter and compress it to densities that shouldn't be possible, creating conditions so extreme that the very concept of a particle starts to lose meaning, and the fundamental building blocks of reality reveal themselves in their purest form, stripped of all the layers of structure that normally hide them from view. And that glimpse into the heart of matter is what makes the Forbidden Zone worth studying, worth investing in new telescopes and detectors, worth developing new theoretical tools, because the answer to what's really there isn't just about neutron stars. It's about understanding the deepest level of physical reality and how the universe puts itself together from the ground up. The Hyperon Puzzle is one of those beautiful moments in physics where theory and observation collide so directly that you can't ignore the problem anymore, where the equations tell you one thing with absolute certainty and the universe shows you something completely different, and suddenly you realize that something fundamental is missing from your understanding of how matter works at extreme densities. The puzzle starts with a simple prediction rooted in well-established nuclear physics, which says that at the densities found in neutron star cores, somewhere around 2 to 3 times nuclear saturation density, it should become energetically favorable for hyperons to appear. And hyperons are these exotic cousins of protons and neutrons that contain strange quarks instead of only the up and down quarks that make up ordinary matter. And the reason they should appear is basically quantum mechanics and thermodynamics working together to find the lowest energy configuration for the system. When you pack neutrons together at enormous densities, the Pauli exclusion principle kicks in hard, because you can't put two identical fermions into the same quantum state. So as you add more and more neutrons, they have to occupy higher and higher energy levels, and eventually it becomes cheaper in terms of energy to convert some of those high-energy neutrons into different types of particles, like hyperons. Because even though hyperons are intrinsically more massive than neutrons, the reduction in degeneracy pressure you get by having multiple types of particles available to fill different quantum states can offset the mass energy cost. And this is the same principle that governs why stars fuse heavier elements, even though it costs energy, because the overall system finds a lower energy state. The main hyperons that theory predicts should show up include lambda particles, which have one strange quark, along with an up quark and a down quark; sigma particles, which come in 3 charge varieties, depending on whether they have 2 up quarks, 2 down quarks, or 1 of each; and cascade particles, which are even stranger because they contain 2 strange quarks and only 1 up or down quark, and each of these particles has different mass and different interactions with neutrons and protons. But all of them share the property that once they start forming in significant numbers, they provide additional degrees of freedom that allow the system to lower its pressure. And here's where the problem starts, because lower pressure means the equation of state softens, meaning the matter becomes more compressible and less able to resist gravitational collapse. When physicists first calculated what would happen if hyperons formed in neutron star cores back in the 1980s and 90s, using the best available models of hyperon-nucleon interactions, which were constrained by scattering experiments and studies of hypernuclei, where single hyperons are bound inside atomic nuclei, they found that the maximum mass a neutron star could support dropped dramatically from around 2.3 solar masses for pure neutron matter down to something like 1.3 to 1.5 solar masses once you included hyperons. And the reason is straightforward. Hyperons soften the equation of state so much that beyond a certain mass, the pressure simply isn't sufficient to hold the star up against gravity, and it collapses into a black hole. So if the theory was right, then no neutron stars heavier than about 1.5 solar masses should exist anywhere in the universe, because they would all have collapsed already. For a while, this prediction seemed fine, because the measured masses of known neutron stars were mostly in the range of 1.4 solar masses, which is the typical mass you get from stellar evolution models, when a massive star explodes as a supernova and leaves behind a neutron star remnant. But then in the early 2000s, astronomers started finding neutron stars that were definitely heavier than the hyperon models predicted, and the observations kept getting more precise and more definitive, until there was no way to dismiss them as measurement errors or statistical flukes. The breakthrough came with the discovery of Pulsar J1614-2230, a millisecond pulsar in a binary system, where precise timing measurements allowed astronomers to determine its mass with remarkable accuracy, and the result was 1.97 plus or minus 0.04 solar masses, which is unambiguously above the 1.5 solar mass limit that most hyperon models predicted. And this was just the beginning, because shortly after that came the discovery of Pulsar J0348 plus 0432, another millisecond pulsar whose mass was measured at approximately 2.01 solar masses. And then the real killer blow to the simple hyperon models came with Pulsar J0740 plus 6620, which clocks in at a whopping 2.14 solar masses, with an uncertainty so small that there's absolutely no doubt it exceeds 2 solar masses. And the existence of these massive neutron stars creates an immediate and unavoidable contradiction with the theoretical predictions. Because if hyperons form the way we think they should, then these stars simply cannot exist. They should have collapsed into black holes long ago. So either hyperons don't form in neutron star cores despite all the theoretical arguments that say they should, or there's something wrong with how we're modeling the hyperon-nucleon interactions, or there's some additional physical effect that we're not accounting for that stiffens the equation of state and compensates for the softening caused by hyperons. The Hyperon Puzzle is particularly frustrating because, unlike some astrophysical mysteries where we're just waiting for better telescopes or more sensitive detectors, this one involves fundamental nuclear physics that should in principle be accessible through laboratory experiments. But the problem is that hyperons are incredibly short-lived particles that decay in less than a nanosecond under normal conditions, which makes it almost impossible to perform the kind of detailed scattering experiments that would let us measure hyperon-nucleon interactions with the precision we need to make reliable predictions about what happens in neutron star cores. The entire database of hyperon-nucleon scattering events, collected over decades of particle physics experiments, consists of only about 1,000 to 1,300 events, which is a pathetically small sample compared to the millions of nucleon-nucleon scattering events we have data for, and the quality of those hyperon events is generally poor with large uncertainties and systematic errors. So when theorists try to construct models of how hyperons interact with neutrons and with each other, they're working with extremely limited experimental constraints and have to make educated guesses about many of the interaction terms, which means the predictions for neutron star properties are much less reliable than we'd like them to be. One possible solution to the Hyperon puzzle that's gained a lot of traction in recent years involves hyperonic three-body interactions, which are forces that act between three particles simultaneously rather than just between pairs. And three-body forces are already known to be important in ordinary nuclear physics because they're necessary to properly describe the binding energies of nuclei and the saturation properties of nuclear matter. So it's natural to expect that similar three-body forces should exist involving hyperons, like neutron-hyperon interactions, or neutron-hyperon-hyperon interactions. And the key insight is that these three-body forces could be repulsive, meaning they push particles apart and increase the pressure, which would stiffen the equation of state and counteract the softening effect of the hyperons themselves. And if the three-body repulsion is strong enough, it could allow neutron stars to reach masses above 2 solar masses, even with hyperons present in the core. The problem is that hyperonic three-body interactions are even more poorly constrained by experiments than two-body interactions because you need even more exotic collision events to measure them. And while there's some indirect evidence from hypernuclear physics that suggests these forces exist and are repulsive, the magnitude and density dependence are highly uncertain, which means theorists have a lot of freedom to adjust the parameters of their three-body force models to fit the observed neutron star masses. But this feels a bit like fine-tuning and doesn't give us much confidence that we really understand what's going on at a fundamental level. Another proposed solution involves momentum-dependent interactions, where the force between a hyperon and a nucleon depends not just on how far apart they are, but also on how fast they're moving relative to each other. And recent work has shown that if you include momentum dependence in the hyperon potentials in a way that's consistent with what we know from microscopic theories of the strong force, you can generate threshold effects that suppress the formation of hyperons at the densities relevant to neutron star cores, essentially pushing the hyperon appearance to higher densities than the simple models predict. And this could allow stars to reach 2 solar masses or more before hyperons become abundant enough to soften the equation of state significantly. The momentum-dependent approach is appealing because it's grounded in fundamental physics rather than being an ad hoc fix, but it still requires making assumptions about the form of the momentum dependence and the strength of the interactions that aren't fully constrained by available data. So while it's a promising direction, it's not yet a definitive solution. Some researchers have suggested that the Hyperon puzzle might be telling us something even more radical about the interior of neutron stars, that maybe instead of hadronic matter with hyperons, we should be thinking about quark matter, where the neutrons and hyperons have completely broken down into their constituent quarks. And in some quark matter models, the equation of state can be stiff enough to support high masses because the interactions between quarks at high density can be strongly repulsive due to effects from quantum chromodynamics that aren't present in hadronic models. And this would essentially bypass the Hyperon puzzle by saying that hyperons never form in the first place, because the matter transitions directly from neutron-rich, hadronic matter to deconfined quark matter at some critical density, skipping over the intermediate region where hyperons would dominate. The challenge with quark matter solutions is that they come with their own set of uncertainties about the quark-quark interactions at neutron star densities, and about the nature of the phase transition between hadronic and quark phases. So you're trading one set of unknowns for another, although some physicists argue that quark matter models are actually more theoretically solid because quantum chromodynamics is a better understood theory than the effective hadronic theories we use to describe nuclear forces, even if QCD itself is difficult to calculate within the relevant densities. The Hyperon puzzle also connects to broader questions about the nuclear force and the strong interaction, because hyperons are just the tip of the iceberg when it comes to strange baryons, and understanding how strangeness enters dense matter is crucial for understanding the full phase diagram of quantum chromodynamics, which describes all the possible states that quarks and gluons can arrange themselves into under different conditions of temperature and density. And neutron stars are unique laboratories for exploring the high-density, low-temperature corner of this phase diagram that's inaccessible to heavy ion collision experiments, which probe high density and high temperature but can't maintain those conditions long enough for matter to settle into its true ground state. Recent observations from gravitational wave detections have added another dimension to the Hyperon puzzle, because when two neutron stars merge, they produce gravitational waves that encode information about the tidal deformability of the stars, which is a measure of how easily they get stretched and squashed by tidal forces. And tidal deformability is directly related to the stiffness of the equation of state, with softer equations of state producing more deformable stars and stiffer equations of state producing less deformable stars. And the gravitational wave event GW 170817, which was the first observed neutron star merger, provided a measurement of tidal deformability that favors relatively stiff equations of state, which is consistent with not having hyperons, or at least not having them in large numbers. But the constraints aren't tight enough yet to completely rule out all hyperon models, especially those with strong three-body repulsion or momentum-dependent interactions that stiffen the equation of state. The cooling behavior of neutron stars also factors into the Hyperon puzzle, because hyperons affect how efficiently the star loses heat through neutrino emission, and different types of hyperons enable different neutrino production mechanisms that can dramatically change the cooling rate. So by observing how quickly young neutron stars cool down, we can potentially infer whether hyperons are present in the core, but the interpretation is complicated by all the other factors that influence cooling, like the pairing gaps in superfluid neutrons and superconducting protons, the thermal conductivity of the crust, and the strength of the magnetic field. So while cooling observations provide valuable constraints, they don't give us a smoking gun that definitively proves or disproves the presence of hyperons. One of the most promising avenues for resolving the Hyperon puzzle involves future experiments at facilities like the Jefferson Lab in Virginia and the Japan Proton Accelerator Research Complex, which are developing new techniques to study hyperon-nucleon interactions using high-intensity beams and sophisticated detectors. And the goal is to dramatically expand the database of hyperon scattering events and to make precise measurements of hyperon production, cross-sections, and interaction strengths that can be used to construct much more reliable theoretical models. And some of these experiments are also looking at the properties of hypernuclei in greater detail, using electromagnetic probes to map out the energy levels and transition rates with unprecedented precision, which provides indirect information about how hyperons interact with nucleons in a dense medium. Although there are always complications in translating what you see in a hypernucleus with atomic number around 10 or 20 to what happens in a neutron star with a baryon number of 10 to the 57th power. The Hyperon puzzle is also driving theoretical work in lattice quantum chromodynamics, where researchers are using supercomputers to solve the equations of QCD numerically on a discrete space-time grid and calculate interaction potentials between baryons from first principles without relying on experimental input. And recent lattice QCD calculations have started to provide some constraints on hyperon-nucleon interactions, although the calculations are extremely demanding computationally and currently can only be done at unphysical quark masses that are heavier than the real-world values. So there's still a significant extrapolation required to get to physical predictions. But the rapid progress in computing power and algorithm development means that within the next decade, we might have lattice QCD predictions for hyperon interactions that are accurate enough to make definitive statements about whether hyperons should form in neutron star cores and what their effect on the equation of state would be. Another piece of the puzzle involves better measurements of neutron star radii, because the radius is just as important as the mass in constraining the equation of state. And while mass measurements for pulsars in binary systems can be extremely precise thanks to the timing method, radius measurements are much more difficult because they require modeling the X-ray emission from the surface, disentangling the effects of temperature, magnetic field, composition, and general relativistic light bending. But NASA's NICER mission, which is mounted on the International Space Station, has been making tremendous progress in this area by observing the X-ray pulsations from rotating neutron stars and using sophisticated Bayesian analysis techniques to simultaneously constrain the mass and radius, and early results from NICER observations of pulsars like J0, 03, 0 plus 04, 51 and J0702 plus 4, 343 have started to narrow down the allowed range of equations of state, showing that neutron star radii are probably in the range of 11 to 13 kilometers for a 1.4 solar mass star, which rules out both the very soft equations of state that would give small radii and the extremely stiff equations of state that would give large radii. And as NICER observes more pulsars, the constraints will get tighter and tighter until eventually we should be able to say with confidence whether hyperons are present or not based on the mass-radius relationship. The Hyperon Puzzle matters beyond just understanding neutron stars because it's fundamentally about testing our understanding of the strong nuclear force in regimes that we can't access any other way. And if we can't correctly predict something as basic as whether hyperons form in dense matter, then it means we're missing crucial pieces of nuclear physics that have implications for everything from how heavy elements are synthesized in neutron star mergers to how matter behaved in the early universe when the entire cosmos was at similar densities. And conversely, if we can solve the Hyperon puzzle by identifying the correct form of hyperonic interactions, then we'll have validated our theoretical framework in one of the most extreme environments possible, which would give us confidence in using similar approaches to study other exotic states of matter, like color superconductivity in quark matter, or the restoration of chiral symmetry at high density. The current state of the Hyperon puzzle is that it remains unsolved, but we're making progress on multiple fronts, with some combination of three body forces, momentum dependence, and possibly phase transitions to quark matter likely being part of the answer. And the next few years should see major advances as new gravitational wave detections accumulate, as NICER continues to measure more neutron star radii, as laboratory experiments at Hyperon facilities start to provide better interaction data, and as theoretical calculations using lattice QCD and advanced many-body techniques become more precise and more reliable. And when we finally do solve the puzzle, it's going to require a synthesis of all these different approaches, because the answer isn't going to come from any single observation or calculation, but from the convergence of evidence from multiple independent sources, all pointing toward the same conclusion about what's really happening inside these incredible objects. The Hyperon puzzle is a perfect example of how modern astrophysics works, where observations of distant objects that we can never visit or directly sample are combined with laboratory experiments on fundamental particles, sophisticated theoretical calculations that push the limits of our computers, and deep insights from quantum field theory to build up a picture of physical conditions that are literally impossible to reproduce on Earth. And the fact that we're even close to solving this puzzle is a testament to how far physics has come and how powerful our tools have become. But it's also a reminder that the universe still has plenty of surprises left and that even our best theories can run into trouble when you push them to extremes, which is exactly why we need to keep observing, keep experimenting, and keep calculating until we finally crack this particular nut and understand once and for all whether hyperons lurk in the hearts of neutron stars, or whether nature has found some other way to pack matter together at densities that stretch the very fabric of physical law. The connection between neutron star cores and the earliest moments of the universe isn't just a metaphor or a loose analogy. It's a direct physical link based on the fundamental reality that the densities and conditions found deep inside these stellar remnants are the closest thing we have in the present-day universe to what existed everywhere during the first microseconds after the Big Bang, when the entire cosmos was compressed into a state so extreme that matter as we know it couldn't exist, and instead, everything was a roiling soup of quarks and gluons, freely interacting without being confined inside protons and neutrons. In those earliest moments, roughly 1 to 10 microseconds after the initial singularity, the temperature of the universe was on the order of 1 trillion degrees Kelvin, and the density was comparable to or even higher than what we now find in the cores of the most massive neutron stars, which means that if quark matter really does exist at the center of these objects, then we're literally looking at a frozen remnant of the primordial state, a piece of the early universe that has somehow survived to the present day, preserved by gravity and pressure, in these tiny cosmic time capsules scattered throughout the galaxy. The Big Bang scenario, as we understand it, describes a universe that began in an incredibly hot and dense state and has been expanding and cooling ever since. And during the first fraction of a second after the beginning, there was no ordinary matter at all, just a quark, gluon plasma, where quarks of all flavors, up, down, strange, charm, bottom, and top, along with their antimatter counterparts and the gluons that mediate the strong force between them, existed in thermal equilibrium, constantly being created and annihilated in the intense heat. And this plasma was so energetic that particles couldn't bind together into composite objects, because any bound state that formed would immediately be torn apart by collisions with other high-energy particles. As the universe expanded and cooled, it went through a series of phase transitions, where the properties of matter fundamentally changed. And one of the most important of these transitions is the confinement transition, also called the hadronization transition, which occurred when the temperature dropped below approximately 150 to 200 million electron volts, which in temperature units is about 10 to the power of 12 Kelvin. And at this point, the quark gluon plasma underwent a dramatic transformation, where the quarks suddenly became confined inside hadrons, which are composite particles like protons, neutrons, and mesons. And this happened because the strong nuclear force has the peculiar property that it gets stronger as you try to pull quarks apart. So once the universe cooled below a critical temperature, the binding energy of hadrons became lower than the thermal energy available to break them apart, and it became energetically favorable for quarks to cluster together rather than remain free. This transition from quark gluon plasma to hadronic matter is one of the most significant events in the early universe, because it fundamentally changed the nature of matter and set the stage for everything that came after, including the formation of atomic nuclei during Big Bang nucleosynthesis a few minutes later. And understanding this transition is crucial for cosmology, because it affects things like the production ratios of light elements and the generation of primordial gravitational waves. But the problem is that we can't directly observe what happened during this period, because the universe was opaque to light until much later, when electrons and nuclei combined to form neutral atoms during the epoch of recombination, roughly 370,000 years after the Big Bang. So all our information about the quark-hadron transition comes from theoretical calculations and from experiments at particle accelerators, where heavy ions are smashed together at relativistic speeds to briefly recreate the conditions of the early universe. Facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN have been colliding gold nuclei and lead nuclei at energies high enough to produce tiny droplets of quark gluon plasma that last for only 10 to the power of -20, 3 seconds before expanding and cooling and hadronizing back into ordinary particles. And by studying the debris from these collisions, physicists have been able to confirm that quark gluon plasma really does exist, and to measure some of its properties, like its viscosity and its temperature. But there are crucial differences between the quark gluon plasma created in heavy ion collisions and what existed in the early universe, or what might exist in neutron star cores, because the collisions produce plasma at very high temperature and relatively low density, whereas the early universe and neutron star cores involve high density at lower temperature. And these different regions of the QCD phase diagram, which is the map showing what states of matter exist under different combinations of temperature and density, can have very different properties and potentially different types of phase transitions. The possibility that neutron star cores contain quark matter means that these objects could be probing the same region of the QCD phase diagram that the universe passed through during the quark-hadron transition, except instead of being a transient state that existed for microseconds and then disappeared forever, the quark matter in neutron stars would be stable and long-lived, held in place by the enormous gravitational pressure and protected from hadronizing by the extreme density. And this would give us a unique laboratory for studying the physics of the early universe, using objects that we can observe with telescopes and gravitational wave detectors, rather than having to rely solely on particle accelerator experiments that can only access these conditions for infinitesimal fractions of a second. The nature of the phase transition between hadronic matter and quark matter is one of the biggest open questions in QCD, because depending on the quark masses and the number of quark flavors involved, the transition could be either first order, where there's a sharp boundary with distinct phases coexisting and latent heat being absorbed or released, or it could be a smooth crossover where the properties change gradually without any discontinuous jump. And lattice QCD calculations suggest that at zero baryon density, which is relevant for the early universe, right after the Big Bang, when matter and antimatter were in equal proportions, the transition is actually a crossover rather than a true phase transition. But at high baryon density, which is what you have in neutron stars, where there's far more matter than antimatter, the situation is less clear, and some models predict that the transition becomes first order, which would have dramatic consequences for neutron star structure, because it would mean there could be a density discontinuity in the core, where the pressure suddenly jumps as you transition from hadronic to quark phase. If the phase transition is first order, then hybrid stars become possible, which are neutron stars with a hadronic outer core surrounding a quark matter inner core. And depending on the exact parameters of the equation of state, there could be interesting phenomena like twin stars, which are two stable configurations with the same mass but different radii, one being a pure hadronic star and the other being a hybrid star with a quark core. Or there could be multiple branches of stability, allowing for more than two solar masses to be supported, even with relatively soft equations of state. And detecting the signatures of these exotic configurations would be a major breakthrough, because it would tell us definitively that we've found quark matter and that neutron stars really do contain echoes of the Big Bang. The quark matter that might exist in neutron star cores isn't necessarily the same as the quark gluon plasma produced in heavy ion collisions, because at the temperatures relevant to neutron stars, which are at most a few billion degrees during the first few minutes after birth, and then drop rapidly to millions or even thousands of degrees as the star ages, the quarks can form correlated states where they pair up similar to how electrons pair up in superconductors, or how neutrons pair up in superfluids. And these color superconducting phases of quark matter are predicted by QCD to be the true ground state at high density and low temperature, meaning they're what you'd expect to find in the core of a neutron star rather than the hot, uncorrelated plasma that exists in collider experiments or in the early universe. Color superconductivity is a fascinating state of matter where quarks of different colors, which is the charge associated with the strong force, analogous to electric charge in electromagnetism, form Cooper pairs that carry zero net color charge, and depending on the density and the quark masses involved, there are several possible color superconducting phases with exotic names like the color flavor locked phase, the two flavor superconductor phase, and the crystalline color superconducting phase, each with different patterns of quark pairing and different physical properties. And if any of these phases exist in neutron star cores, they would affect the equation of state, the cooling behavior, the neutrino emissivity, and potentially the magnetic field structure in ways that might be observable with current or future telescopes. One of the most intriguing aspects of color superconductivity is that it can make the equation of state stiffer, meaning the matter becomes harder to compress, which helps resolve the problem of how to support neutron stars with masses above 2 solar masses. And this happens because the pairing energy of the color superconducting state lowers the free energy of the system and allows it to resist compression more effectively than unpaired quark matter would. So in some sense, color superconductivity acts like the three-body repulsion in Hyperon models, providing an additional source of pressure that stiffens the equation of state and allows higher maximum masses. And this means that finding very massive neutron stars doesn't necessarily rule out quark matter. It just constrains what types of quark matter phases are possible. The connection to the Big Bang becomes even more direct when we consider neutron star mergers, which are events where two neutron stars in a binary system spiral together and collide, producing a kilonova explosion that's visible across the electromagnetic spectrum and generates gravitational waves that we can detect here on Earth. And during the final moments before merger and in the immediate aftermath, when a hot hypermassive remnant briefly exists before collapsing into a black hole, the temperatures can reach billions of degrees, which is hot enough that even if the original cores were in a cold color, superconducting state, they would be heated above the critical temperature and transition into a hot quark gluon plasma, similar to what existed in the early universe. So these mergers are essentially recreating Big Bang conditions on a local scale and allowing us to probe the same physics that governed the universe's first microseconds. The kilonova observed in August 2017, which was designated a 2017 GFO, and was associated with the gravitational wave event GW170817, provided the first multi-messenger observation of a neutron star merger and gave us unprecedented insight into what happens during these cataclysmic events. And one of the most remarkable findings was that the temperature evolution of the ejected material closely mirrors what happened during the early universe, with the expanding fireball starting at billions of degrees, where matter exists as a plasma of unbound particles, and then cooling over hours and days as it expands, until the temperature drops low enough that electrons can bind to atomic nuclei and form neutral atoms in a process that's directly analogous to the epoch of recombination that occurred 370,000 years after the Big Bang. By observing the light curves and spectra from this kilonova at multiple wavelengths, using telescopes around the world, astronomers were able to track the temperature as a function of time and watch as heavy elements formed in the expanding debris. And the data showed clear signatures of strontium and yttrium, which are elements that can only be created through rapid neutron capture nucleosynthesis, also called the raw process, which requires extremely neutron-rich conditions that don't exist anywhere in the universe today, except during neutron star mergers and possibly during certain types of supernova explosions. And this confirmed that kilonovae are a major source of heavy elements in the universe, and that the matter being ejected includes material from the neutron star cores that has been processed under the most extreme conditions imaginable. The fact that we can observe these miniature Big Bangs happening in real time gives us a unique window into physics that would otherwise be completely inaccessible, because while we can never go back and directly observe what happened in the early universe, we can watch neutron stars collide and measure the properties of the hot, dense matter they produce. And by comparing those measurements to theoretical predictions from QCD and cosmology, we can test whether our understanding of the Quark-Hadron transition and the subsequent evolution of matter in the expanding universe is correct, and any discrepancies between observations and theory would tell us that we're missing something important about how matter behaves at extreme conditions. The possibility of strange quark matter adds another layer to the connection with the Big Bang, because if strange quark matter really is more stable than ordinary nuclear matter, as some calculations suggest, then it raises the question of why the universe ended up being made of protons and neutrons rather than strange quarks. And one answer could be that during the Quark-Hadron transition, the universe cooled and expanded so rapidly that it never had time to settle into the true ground state, and instead got stuck in a metastable state of hadronic matter, which would mean that everything we see around us, all the atoms in our bodies, and in the Earth, and in the stars, is actually just a long-lived excited state that hasn't yet decayed to strange quark matter, because there's a large energy barrier preventing the transition. And if that's true, then neutron stars might be the only objects in the universe where the density and pressure are high enough to overcome that barrier and allow the transition to the true ground state to occur. This scenario leads to the exotic possibility of strange stars, which would be completely stable objects made entirely of strange quark matter from surface to center, with no crust and no hadronic layer at all. And these objects would be even more extreme than neutron stars, with densities approaching or exceeding 10 to the power of 15 grams per cubic centimeter throughout their entire volume. And they could potentially be identified by their unusual properties, like smaller radii for a given mass compared to normal neutron stars, or different cooling curves, or different responses to perturbations. But so far, no confirmed strange stars have been detected, although there are a few candidates with peculiar properties that don't quite fit standard neutron star models and could potentially be explained if they're actually strange stars. The search for quark matter in neutron stars is fundamentally a search for evidence of the early universe's most dramatic transformation, the moment when the primordial soup of quarks and gluons that filled all of space condensed into the hadrons that make up ordinary matter. And if we can prove that this transition is reversible by finding quark matter in neutron star cores, then we'll have demonstrated that the extreme conditions of the Big Bang aren't unique to the first microseconds of cosmic history, but can be recreated by nature through gravitational collapse and maintained indefinitely inside these remarkable objects. The theoretical tools we use to study both neutron stars and the early universe are largely the same. Primarily quantum chromodynamics solved using lattice methods or effective field theories that capture the essential physics without requiring full numerical solutions of the impossibly complex equations, and improvements in our understanding of one domain directly benefit the other. So every time we learn something new about neutron star cores from gravitational wave detections or X-ray observations or pulsar timing, we're also learning something about what happened in the first microseconds after the Big Bang. And conversely, every advance in lattice QCD calculations or in heavy ion collision experiments that probe the properties of dense quark matter helps us make better predictions about what should be inside neutron stars and how to recognize the signatures of exotic phases, if they exist. The densities involved span an enormous range, from normal nuclear saturation density at around 10 to the power of 14 grams per cubic centimeter, which is what you find in the outer core, and which is also comparable to the average density of atomic nuclei, up to potentially 10 times that or more in the inner cores of the most massive neutron stars. And this range encompasses the critical density where the Quark-hadron transition is expected to occur based on theoretical calculations, although the exact threshold depends on temperature and other factors, and is one of the major uncertainties in current models. And part of what makes neutron stars so valuable as laboratories is that different stars with different masses and different thermal histories may be probing different parts of this density range. So by observing a population of neutron stars with varying properties, we can map out the equation of state as a function of density and potentially identify the signature of phase transitions or the appearance of new states of matter. Gravitational waves from neutron star mergers carry information encoded in the tidal deformability about how easily the stars distort under extreme gravitational stress. And this tidal deformability is exquisitely sensitive to the stiffness of the equation of state, which in turn depends on what phases of matter are present in the core. And as the LIGO, Virgo, and CAGRA detectors continue to observe more mergers, over the coming years, we'll build up a statistical sample that will allow us to place increasingly tight constraints on the allowed range of equations of state. And if we're lucky, we might even detect a post-merger remnant that survives for a few milliseconds before collapsing into a black hole, because this remnant would be spinning at incredible rates and emitting gravitational waves at kilohertz frequencies that would carry direct information about the structure of hot, rapidly rotating hypermassive neutron stars that are temporarily supported against collapse by centrifugal forces. And these objects would be probing the absolute maximum density that matter can achieve before it must inevitably become a black hole. The echo of the Big Bang that we hear in neutron star cores isn't literal sound, obviously, but it's a resonance of physical conditions, a recreation of the same extreme states of temperature and density and pressure that defined the universe's beginning. And just as cosmologists study the cosmic microwave background radiation to learn about the universe when it was 370,000 years old, astrophysicists study neutron stars to learn about conditions that existed when the universe was microseconds old. And in both cases, we're using the tools of modern physics, quantum field theory and general relativity and statistical mechanics to extract information about the past from signals that reach us in the present. The ultimate goal is to achieve a complete understanding of the QCD phase diagram, mapping out all the possible states of quark and gluon matter under every combination of temperature and density. And neutron stars provide crucial data points in the high-density, low-temperature corner of this diagram that can't be accessed by any other means, while heavy ion collisions probe the high-temperature, moderate-density region, and cosmological observations constrain what happened along the cooling trajectory that the early universe followed as it expanded. And by combining all these different sources of information, we're gradually filling in the picture and discovering where the boundaries between different phases lie and what the properties of each phase are. The fact that such extreme physics is accessible through astronomical observations of objects that are typically thousands or millions of light years away is one of the beautiful paradoxes of modern astrophysics, that we can learn about the smallest scales of matter, the interactions between quarks that take place over distances of 10 to the power of minus 15 meters, by observing the largest scales of cosmic phenomena like gravitational waves rippling across the universe, or light from merger events that release more energy in a few seconds than the sun will emit in its entire lifetime. And the connection between these scales is gravity, which on one hand is the weakest of the fundamental forces, but on the other hand is the only force that can compress matter to such extreme densities that it forces the strong nuclear force to reveal its most exotic behaviors. Neutron stars are teaching us that the universe still contains pockets where the conditions of the Big Bang persist, not as a temporary state during collisions or explosions, but as a permanent fixture of the cosmic landscape, protected and preserved by gravity inside these stellar corpses that will continue to exist for trillions of years long. After all the normal stars have burned out and the galaxy has gone dark, and if quark matter really exists in their cores, then these objects are literally carrying forward a piece of the primordial universe, a fragment of the original state from which everything emerged, and studying them is as close as we can come to peering back through time to witness the moment of creation. The greatest frustration in studying neutron star cores is that we can never go there, can never drill down through the layers to collect a sample, can never place instruments directly into the interior to measure the temperature and pressure and composition. So everything we know about what's happening inside these objects has to be inferred from the faint signals they send us across the vast distances of space. And reading those signals correctly requires an intricate dance between observation and theory, where astronomers use telescopes to measure properties like brightness and timing and spectral features, while theorists build models that predict what those measurements should look like if the core contains hyperons or quark matter or superfluids. And by comparing the observations to the predictions, we gradually narrow down the possibilities until hopefully we converge on the truth. The primary tools we have for reading neutron star signals fall into several categories, each probing different aspects of the star's structure and composition. And the first and most established method is pulsar timing, which has been refined over decades into an extraordinarily precise technique that can measure the rotation rate of a neutron star to 15 or 16 decimal places, allowing astronomers to detect changes in the spin period as small as a few nanoseconds per year. And this precision is crucial because the way a pulsar spins down over time depends directly on how the star is losing energy, whether through magnetic dipole radiation, where the spinning magnetic field creates electromagnetic waves that carry energy away, or through gravitational wave emission, if the star has any asymmetry or deformation that causes it to generate ripples in space-time as it rotates, or through other processes like particle winds or accretion. And by measuring the spin-down rate with extreme accuracy, we can determine what mechanisms are at work and make inferences about the star's magnetic field strength, its moment of inertia, and potentially its internal structure. Pulsar glitches provide another window into the interior, because these sudden jumps in rotation rate, where the star speeds up by a tiny fraction over the course of seconds or minutes before gradually relaxing back to its previous spin-down rate, are thought to be caused by the interaction between the superfluid layers in the core and the solid crust. And the basic idea is that as the crust spins down due to magnetic braking, the superfluid interior doesn't immediately follow because it's not rigidly coupled to the crust. So angular momentum builds up in the superfluid until eventually there's a sudden transfer event, possibly triggered by the unpinning of vortices in the superfluid, or by a starquake where the crust fractures and suddenly changes shape. And this transfer of angular momentum from the interior to the crust causes the observed speed up. And by studying the magnitude of the glitch, the relaxation timescale, and the frequency of glitches in different pulsars, we can learn about the superfluid properties, the coupling strength between the crust and core, and the distribution of angular momentum within the star. The Vela pulsar is the poster child for glitch studies because it glitches roughly every 3 years with remarkably consistent characteristics, and observations stretching back decades have allowed astronomers to build detailed models of its interior structure and to test theories of superfluid dynamics against real data. But other pulsars, like the Crab pulsar and PSRJ 0537-6910, also show interesting glitch behavior with different characteristics that suggest variations in internal structure from one neutron star to another, possibly reflecting differences in mass or age or thermal history that affect how the superfluid forms and how it couples to the crust. Mass measurements are absolutely critical for constraining the equation of state because the maximum mass a neutron star can support is directly determined by how stiff or soft the core is, with stiffer equations of state allowing higher masses before gravitational collapse becomes inevitable. And the gold standard for mass measurements comes from binary pulsars where the neutron star is orbiting another compact object, like a white dwarf or another neutron star, and the orbital dynamics give you precise information about both masses through general relativistic effects, like the Shapiro delay, where the light from the pulsar is delayed when it passes close to the companion, or through the measurement of post-Keplerian parameters, like the rate of periastron advance, which depends on the masses in a way that can be precisely calculated using general relativity. And when you combine multiple independent measurements of different relativistic effects, you can solve for both the pulsar mass and the companion mass, with uncertainties as small as a few percent, or even less in the best cases. The classic example is the Hulse-Taylor binary pulsar PSRB 1913+16, where decades of timing observations have measured the masses to exquisite precision and have also provided the first indirect evidence for gravitational waves by showing that the orbit is decaying at exactly the rate predicted by general relativity. If the system is losing energy to gravitational radiation, and more recently, systems like PSRJ 0348 plus 0432 and PSRJ 0740 plus 6620 have pushed the mass measurements to over 2 solar masses, which has been revolutionary for constraining neutron star models, because it immediately rules out any equation of state that predicts a maximum mass below what's observed. And every time a new record holder is discovered, it forces theorists to go back and revise their models to account for the higher mass. Radius measurements are equally important because the mass alone doesn't uniquely determine the equation of state. You need both mass and radius together to pin down the relationship between pressure and density. But radius measurements are much more difficult than mass measurements because you have to observe thermal emission from the surface and then model the spectrum, accounting for the temperature distribution, the atmospheric composition, the gravitational redshift and light bending effects from general relativity, and the distance to the star. And each of these factors introduces uncertainty that propagates into the final radius estimate. So for many years, radius measurements were too imprecise to provide strong constraints on the equation of state. But that changed dramatically with the launch of NASA's Neutron Star Interior Composition Explorer, known as NICER, which is an X-ray telescope mounted on the International Space Station specifically designed to make precise measurements of neutron star radii by observing the X-ray pulsations from millisecond pulsars and using the modulation pattern as the star rotates to infer both its size and its mass simultaneously. The key insight behind NICER is that as a hot spot on the neutron star surface rotates in and out of view, the X-ray flux varies in a way that depends on the star's compactness, which is the ratio of mass to radius. And by carefully modeling the pulse profile using sophisticated Bayesian inference techniques that account for all the relevant physics, including general relativistic ray tracing of photons in the curved spacetime around the star, you can extract both the mass and radius with uncertainties small enough to start distinguishing between competing equations of state. And the first results from NICER observations of PSRJ 0030 plus 0451 showed that the radius is around 13 kilometers for a mass of about 1.4 solar masses, which favors relatively stiff equations of state and disfavors the softest models that would give radii below 11 kilometers. And subsequent observations of PSRJ 0702 plus 4343 have provided additional constraints that are helping to narrow down the allowed range of equations of state even further. Gravitational wave detections have opened up an entirely new way to probe neutron star interiors, because when two neutron stars spiral together and merge, they produce gravitational waves whose properties encode information about the star's internal structure, and the key observable is tidal deformability, which measures how easily the star gets distorted by the tidal forces from its companion during the final stages of the inspiral before merger. And this tidal deformability depends directly on how compressible the matter is, with softer equations of state producing larger deformations and stiffer equations of state producing smaller deformations. And these tidal effects leave a measurable imprint on the gravitational wave signal in the form of a deviation from the pure point mass waveform that you'd get if the objects were black holes. So by analyzing the waveform with matched filtering techniques and comparing it to theoretical templates that include tidal effects, you can measure the tidal deformability and use it to constrain the equation of state. The breakthrough event was GW1708-17 detected on August 17, 2017 by the IGO and Virgo detectors, which was the first observation of a binary neutron star merger and provided the first direct measurement of tidal deformability from gravitational waves. And the analysis of that signal placed upper limits on how large the tidal deformability could be, which translated into constraints on the equation of state that ruled out very stiff models that would produce highly deformable stars. And when combined with the existence of two solar mass neutron stars, which rule out very soft equations of state, the tidal deformability measurement from GW1708-17 helped to narrow the allowed range considerably, pushing us toward intermediate stiffness models. And as more neutron star mergers are detected in future observing runs, the statistical precision of these constraints will continue to improve. And there's also the exciting possibility of detecting gravitational waves from the post-merger remnant if it survives for a few milliseconds before collapsing into a black hole, because this remnant would be oscillating and producing gravitational waves at kilohertz frequencies that would carry direct information about the equation of state at the highest densities reached anywhere in the universe. Electromagnetic observations of neutron star mergers, particularly the Kilonova emission that comes from radioactive decay of heavy elements synthesized in the merger ejecta, provide complementary information because the properties of the Kilonova depend on how much mass is ejected during the merger and what its composition is, and both of these factors are influenced by the equation of state, with softer equations of state generally leading to more ejecta because the stars are larger and more easily disrupted, while stiffer equations of state produce less ejecta because the stars are more compact and hold together better until the final moment. And by observing the Kilonova light curve at multiple wavelengths over days and weeks as it fades and cools, astronomers can infer the mass and composition of the ejecta and use that to constrain the equation of state. And the Kilonova associated with GW1708-17, designated at 2017 GFO, was observed by telescopes around the world in optical, infrared, ultraviolet, and X-ray wavelengths, providing an unprecedented data set that confirmed the production of heavy elements through the raw process and gave estimates of the ejecta mass that were consistent with the equation of state constraints from the gravitational wave signal. Cooling observations provide another avenue for probing the interior, because young neutron stars born in supernova explosions start out incredibly hot, with core temperatures potentially reaching billions of degrees, and they cool over time by emitting neutrinos from the interior and photons from the surface. And the cooling rate depends sensitively on what's happening in the core, because different particle interactions produce different neutrino emission processes with vastly different efficiencies. And if the core contains exotic matter like hyperons or quark matter, or if it undergoes phase transitions, or if superfluidity and superconductivity develop, All of these can dramatically affect the cooling curve. So by observing the surface temperature of neutron stars of known age, we can test theoretical cooling models and infer what must be present in the core to match the observations. The most famous cooling observation is of the neutron star in the Cassiopeia, a supernova remnant, which is about 340 years old, based on when the supernova light reached Earth, and observations with the Chandra X-ray Observatory. Over a 10-year period from 1999 to 2009 showed that the surface temperature dropped by about 4%, which sounds small, but is actually a surprisingly rapid decline that caught theorists off guard because standard cooling models predicted much slower temperature changes. And the best explanation for the rapid cooling is that the core underwent a transition to superfluidity during the observation period, with neutrons suddenly pairing up into Cooper pairs throughout a large volume of the core, and the formation of the superfluid causes a brief pulse of enhanced neutrino emission through a process called pair breaking and formation, where neutrinos are produced as the paired state establishes itself. And this neutrino pulse carries away energy rapidly, causing the accelerated surface cooling that was observed. And this interpretation is supported by detailed simulations that show the timing and magnitude of the cooling are consistent with superfluid formation in a neutron star of Cassiopeia A's age and mass, making this one of the strongest pieces of observational evidence we have that neutron star cores really do contain superfluid matter. Other cooling observations include surveys of young neutron stars and supernova remnants of various ages, which show a range of temperatures that need to be explained by cooling models. And some stars cool faster than standard models predict, while others cool more slowly. And these variations might reflect differences in internal composition or structure, with faster cooling possibly indicating the presence of exotic particles that open up additional neutrino emission channels, while slower cooling might suggest strong superfluidity or other effects that suppress neutrino emission. But interpreting these observations is complicated by uncertainties in the star's ages, their initial temperatures, the properties of their crusts, which act as insulating blankets, and their magnetic field strengths, which can affect surface temperature distributions. Continuous gravitational wave searches are looking for signals from rapidly spinning neutron stars that have some kind of asymmetry or deformation that causes them to emit gravitational waves steadily as they rotate, like a cosmic lighthouse, but with space-time ripples instead of light. And if such a signal were detected, it would provide incredibly valuable information about the star's moment of inertia and its internal structure, because the gravitational wave amplitude depends on both the size of the deformation and how the mass is distributed inside the star. And by combining the gravitational wave signal with electromagnetic observations of the same pulsar, you could potentially measure the moment of inertia directly, which would give powerful constraints on the equation of state, since the moment of inertia is very sensitive to how centrally concentrated the mass is. But despite years of searching with LIGO and Virgo, no continuous gravitational waves from neutron stars have been definitively detected yet, which places upper limits on how deformed these stars can be, and tells us that mountains on neutron star surfaces can't be very high, probably no more than a few millimeters or centimeters, even though the crust is strong enough to support much larger deformations. And this suggests that whatever mechanism creates mountains, whether it's magnetic stresses or accretion, or leftover asymmetries from the formation process, is quite limited in its ability to deform these objects. The challenge with all these different observational techniques is that each one has its own systematic uncertainties and potential biases, and the theoretical models used to interpret the observations also have uncertainties that come from incomplete knowledge of nuclear physics at extreme densities. So you can't just take a single observation and definitively prove what's in the core. Instead, you need to combine multiple independent observations using different techniques and look for consistency across the board. And when all the different methods point toward the same conclusion, then you can have confidence that you're getting close to the truth. But if different observations seem to favor incompatible models, then it means either the observations are wrong or the theoretical framework is missing something important. And sorting out which is the case requires careful analysis of the uncertainties and often requires waiting for better data or improved theories. The computational challenge of analyzing these signals is enormous because gravitational wave data from merger events contains signals buried in noise that need to be extracted using matched filtering techniques that compare the data to millions of theoretical waveform templates. And this requires massive supercomputer resources running for weeks or months to fully analyze a single event. And even then, there are degeneracies in the parameter space where multiple different combinations of mass, radius, tidal deformability, and equation of state can produce similar waveforms that are hard to distinguish given the noise level in the detectors. So improving the sensitivity of future gravitational wave detectors, like the planned Einstein telescope and Cosmic Explorer, will be crucial for making more precise measurements that can break these degeneracies. Machine learning is increasingly being used to speed up the analysis of gravitational wave signals and to detect events in real time as they occur, rather than having to wait for offline analysis pipelines to process the data. And neural networks can be trained to recognize the characteristic patterns of binary neutron star mergers in noisy data, and to make rapid estimates of source properties like sky location and mass that can be used to alert electromagnetic telescopes to look for the kilonova. And recent developments have shown that machine learning algorithms can achieve inference times of around 1 second for complete parameter estimation, which is fast enough to enable true real-time multi-messenger astronomy, where gravitational wave detections trigger immediate follow-up observations across the electromagnetic spectrum. And this capability will be increasingly important as the network of gravitational wave detectors expands and the detection rate increases from a few events per year, currently to potentially hundreds of events per year in the next decade. The synergy between different observational techniques is where the real power lies, because each method probes complementary aspects of neutron star structure. And by combining them, you get constraints that are much tighter than any single technique could provide. And a beautiful example of this is how the mass measurements from binary pulsars, the radius measurements from NICER, the tidal deformability from gravitational waves, and the cooling observations from X-ray telescopes all point toward equation of state models with intermediate stiffness that allow maximum masses around 2.5 solar masses and radii around 12 to 13 kilometers for typical 1.4 solar mass stars. And this convergence is telling us that we're zeroing in on the right answer, even though we still don't know definitively what exotic particles might be present in the cores. And as the observational data continues to improve and accumulate the constraints, will get tighter and tighter until eventually the uncertainties become small enough that we can say with confidence whether hyperons or quark matter exist in neutron star cores, or whether the cores remain purely hadronic all the way to the center. The next generation of instruments promises to revolutionize our ability to read neutron star signals, with next-generation gravitational wave detectors like Einstein telescope being planned for construction in Europe and Cosmic Explorer being developed in the United States, both of which will be roughly 10 times more sensitive than current detectors and will be able to observe neutron star mergers out to cosmological distances, potentially seeing thousands of events per year instead of dozens. And this flood of data will allow statistical studies of the neutron star population and will provide much tighter constraints on the equation of state by averaging over many independent measurements. And there are also plans for improved X-ray telescopes with larger collecting areas and better timing resolution that could extend the NICER technique to fainter and more distant pulsars. and radio telescope arrays, like the square kilometer array being built in Australia and South Africa, will dramatically improve pulsar timing precision and will be able to detect much weaker pulsars, potentially finding new binary systems with exotic masses or unusual properties that challenge current models. Reading the signals from neutron stars is fundamentally an exercise in detective work, where you gather clues from multiple sources, piece together a narrative that explains all the observations, test that narrative against new data as it comes in, and gradually refine your understanding until the picture becomes clear. And what makes it challenging is that the signals are incredibly faint, the objects are impossibly distant, and the physics governing their behavior involves regimes that we can't access in any laboratory on Earth. But what makes it exciting is that despite all these challenges, we're actually making progress. We're actually learning things about the most extreme matter in the universe by carefully analyzing the photons and gravitational waves that reach us from across the galaxy. And every new observation brings us closer to answering the fundamental question of what exists at the center of these remarkable objects, and whether nature has found a way to recreate the conditions of the Big Bang inside stellar remnants that will outlive all the normal stars in the sky. Despite decades of intensive research involving the world's most powerful telescopes, gravitational wave detectors, particle accelerators, and supercomputers, the simple truth is that we still don't know what exists at the center of a neutron star. And this uncertainty isn't just a minor gap in our knowledge, it's a fundamental blind spot that affects our understanding of nuclear physics, particle physics, and even cosmology. Because the answer to what happens when you compress matter to densities several times higher than atomic nuclei determines not just the structure of neutron stars, but also what happened during the Quark-Hadron transition in the early universe, and potentially what form dark matter takes, and whether there are violations of fundamental symmetries that we haven't detected in laboratory experiments. The equation of state, which is the mathematical relationship between pressure and density that tells you how matter responds to compression, remains one of the biggest unknowns in all of physics. Because at the densities found in neutron star cores, we simply don't have experimental data to constrain the models. And while we've made progress in narrowing down the possibilities by combining observations from multiple sources like pulsar timing, gravitational waves, X-ray spectroscopy, and cooling measurements, the remaining uncertainty is still large enough that multiple competing scenarios remain viable, including pure neutron matter with no exotic particles, hyperonic matter with lambda and sigma particles mixed in, meson condensates, where pions or kaons form collective quantum states, deconfined quark matter, where neutrons break down into their constituent quarks, color superconducting, quark matter, where the quarks pair up in exotic patterns, strange quark matter, where up, down, and strange quarks exist in equal proportions, and hybrid configurations, where different phases coexist in different regions of the core. And each of these possibilities predicts slightly different values for observable properties like maximum mass, radius, tidal deformability, and cooling rate. But the differences are often smaller than the measurement uncertainties, so we can't definitively rule out most of them yet. The maximum mass of a neutron star is directly connected to the equation of state, because a stiffer equation of state that resists compression more strongly can support more mass before gravitational collapse becomes inevitable. And while we've discovered neutron stars with masses exceeding 2 solar masses, which rules out the softest equations of state, we still don't know where the ultimate limit lies, whether it's at 2.2 solar masses or 2.5 solar masses, or even higher. And finding this limit would tell us immediately how stiff the core can be, which would narrow down the allowed types of exotic matter dramatically. But the problem is that neutron stars form with a range of masses determined by the progenitor star's mass and the details of the supernova explosion, and there might not be any neutron stars in the universe that are right at the maximum mass limit. They might all either be well below it, or they might have already collapsed into black holes if they exceeded it. So we could potentially measure hundreds of neutron star masses without ever finding the true maximum. The question of whether hyperons exist in neutron star cores remains unresolved despite decades of theoretical work, because while the basic energetics suggest they should form at densities around 2 to 3 times nuclear saturation density, the interactions between hyperons and nucleons are so poorly constrained by experimental data that we can't make reliable predictions about their abundance or their effect on the equation of state and the Hyperon puzzle, where theoretical models with hyperons predict maximum masses below what's observed, while models without hyperons struggle to explain why they don't form when energetically they should, has multiple proposed solutions involving 3 body forces or momentum-dependent interactions or phase transitions to quark matter that bypass the hyperon regime entirely. But none of these solutions have been definitively confirmed, and each requires making assumptions about physics that we can't test directly in laboratories. So we're left with a situation where hyperons might be a major component of neutron star cores, or they might be completely absent, and both possibilities remain consistent with current observations depending on what assumptions you make about the uncertain interaction terms. The possibility of quark matter is equally uncertain, because while quantum chromodynamics tells us that at sufficiently high-density quarks should become deconfined and form a quark-gluon plasma, the critical density where this transition occurs is unknown and could be anywhere from twice nuclear saturation density to 10 times nuclear saturation density, or even higher, depending on the strength of quark-quark interactions and the details of the confinement mechanism. And complicating matters further is the possibility of color superconductivity, where quarks pair up at low temperature, which could either stiffen or soften the equation of state, depending on which color superconducting phase forms and what the pairing gaps are. And these pairing gaps are incredibly difficult to calculate from first principles using lattice QCD, because they involve subtle quantum correlations at finite density, where current computational methods struggle. So we're relying on approximate calculations and phenomenological models that could be missing important physics. The nature of the phase transition between hadronic and quark matter, if it occurs at all, is another major unknown, because it could be either a first-order transition with a sharp boundary and coexisting phases, or it could be a smooth crossover where the properties change gradually without any discontinuous jump. And lattice QCD calculations suggest that at high temperature and low density, which is relevant for heavy ion collisions, and the early universe, right after the Big Bang, the transition is a crossover, but at high density and low temperature, which is what you have in neutron star cores, the calculations become much more difficult and the results are less certain, and some models predict that the transition becomes first order at high density, which would allow for exotic phenomena like twin stars, where 2 different configurations have the same mass but different radii, or multiple stable branches, where the mass radius curve has kinks and discontinuities. But detecting these features requires measuring masses and radii with precision better than a few percent, which is right at the edge of what current instruments like NICER can achieve. So we need more observations before we can say definitively whether the transition is first order or a crossover. The cooling behavior of neutron stars provides valuable constraints on the interior composition, but the interpretation of cooling observations is plagued by uncertainties about the thermal conductivity of the crust, the strength and geometry of the magnetic field, the initial temperature after the supernova, and the exact neutrino emission processes that operate in the core. And while the rapid cooling observed in the Cassiopeia, a neutron star, strongly suggests that superfluidity is present, we don't know the exact pairing gaps, or whether the entire core is superfluid or just certain regions, and we don't know whether other exotic particles like hyperons or quarks are also present and contributing to the cooling through additional neutrino emission channels. And observations of other young neutron stars show a range of cooling rates that could be interpreted as evidence for compositional differences between stars, or could just reflect variations in their masses, ages, or initial conditions. So untangling all these effects requires not just more cooling measurements, but also better theoretical models that can accurately predict how different combinations of factors affect the temperature evolution. The question of whether strange quark matter is the true ground state of matter at high density has profound implications that go far beyond neutron stars. Because if strange quark matter really is more stable than nuclear matter, then the entire universe might actually be in a metastable state that hasn't yet decayed to the true ground state. And if a neutron star core transitions to strange quark matter and becomes a strange star, it could potentially trigger a chain reaction where normal matter that comes into contact with the strange matter gets converted. Although whether this conversion is energetically favorable and kinetically possible is highly debated, and some theorists have speculated that strange matter from neutron star collisions could be ejected into space as strange nuggets or strangelets that could survive and possibly be detected. But no confirmed strangelets have ever been found, despite searches in cosmic ray detectors and at particle accelerators. So either strange quark matter isn't stable after all, or the conditions required to produce it are more stringent than we thought. The role of superfluidity and superconductivity in neutron star cores is partially understood, but many details remain unclear, including the exact pairing gaps for neutrons and protons in different density regions, whether the pairing is in the singlet channel or the triplet channel, how the pairing interacts with the magnetic field to produce flux tubes and vortices, whether there are multiple superfluid phases with different properties in different layers, and how the superfluid couples to the crust to produce the pulsar glitches that we observe. And while the basic phenomenon of superfluidity is well established through observations of glitches and cooling, the microscopic details matter enormously for making quantitative predictions about things like how much angular momentum is stored in the superfluid versus the crust, or how quickly heat is transported from the core to the surface, or how the magnetic field evolves over millions of years as currents decay and reconnection events occur. And getting these details right requires better calculations of the pairing interactions, using more realistic models of nuclear forces that go beyond simple contact interactions or schematic potentials. The connection between neutron star observations and laboratory nuclear physics experiments is both a strength and a weakness of the field, because on one hand, having two independent sources of information about dense matter allows us to cross-check our theoretical models and build confidence when different approaches give consistent results. But on the other hand, the density and temperature regimes probed by neutron stars and by heavy ion collisions are quite different, with collisions accessing high temperature and moderate density, while neutron stars involve high density and low temperature. And bridging the gap between these regimes requires theoretical extrapolations that introduce their own uncertainties. And moreover, the scattering experiments that measure nuclear forces and hyperon interactions can only access a limited range of energies and angles, and extracting the full interaction potential from the scattering data requires making assumptions about the functional form and fitting parameters that may not be unique. So there's inherent model dependence in translating experimental results into predictions for neutron star properties, and reducing this model dependence requires both better experiments with higher precision and larger coverage of different reactions and energies, and better theoretical methods for connecting the scattering observables to the many-body equation of state. The impact of magnetic fields on neutron star structure is poorly understood, because while we know that some neutron stars have incredibly strong magnetic fields, that rival or exceed the quantum critical field of 4 times 10 to the power of 13 Gauss, where the magnetic energy density becomes comparable to the electron rest mass energy. We don't know how these fields are generated during the formation of the neutron star, whether they're amplified by dynamo processes during the first few seconds after the supernova, or whether they're fossil fields inherited from the progenitor star. And we don't know how the internal magnetic field is distributed, whether it's mostly in the crust or penetrates deep into the core, whether it's primarily poloidal or toroidal, and how it affects the equation of state through magnetic pressure and through its influence on particle interactions. And in magnetars, which have the strongest fields, the magnetic energy is so large that it can potentially deform the star and create mountains on the surface that would emit continuous gravitational waves. But we don't know how large these deformations can be, or how stable they are over time. And the magnetic field evolution over millions of years involves complex processes like ambipolar diffusion and Hall drift and ohmic decay that depend sensitively on the electrical conductivity and the coupling between charged and neutral components. So modeling this evolution accurately requires knowing the composition and superfluid properties throughout the star, which brings us back to the same uncertainties about the equation of state and exotic matter. The question of how neutron stars are born and what determines their initial properties is intimately connected to supernova physics, which remains one of the major unsolved problems in astrophysics. Because despite decades of sophisticated numerical simulations, we still don't fully understand what causes massive stars to explode, or how the explosion dynamics determine the mass and kick, velocity and rotation rate of the resulting neutron star, and different supernova mechanisms like neutrino-driven explosions or magneto-rotational explosions or fallback accretion could lead to neutron stars with different internal structures or different compositions. And there might even be multiple formation channels that produce observationally distinct populations of neutron stars with different properties. But disentangling the formation history from the intrinsic physics of the equation of state requires having large enough samples of neutron stars with well-measured properties that we can look for correlations and patterns. And this is only now becoming possible with the accumulation of gravitational wave detections and X-ray observations and radio timing measurements from multiple instruments operating simultaneously. The possibility of dark matter accumulation in neutron stars is an intriguing open question, because if dark matter particles interact with ordinary matter, even weakly, they could be captured by the neutron star's gravity as they pass through, and over millions of years, a significant amount of dark matter could accumulate in the core, where it would affect the structure and potentially trigger collapse to a black hole if enough accumulates. And some models even propose that dark matter could form a black hole at the center of the neutron star that slowly accretes the surrounding matter from the inside out. But testing these scenarios requires knowing both the properties of dark matter particles, like their mass and cross-section, and the properties of neutron star matter, like the equation of state and the temperature profile. So there are multiple layers of uncertainty, and observationally, the signatures of dark matter in neutron stars could include unusual heating or cooling behavior, unexpected population statistics with too few old neutron stars if they collapse early due to dark matter accumulation, or possibly even exotic electromagnetic signals if dark matter particles annihilate in the core. But so far, no conclusive evidence for dark matter effects in neutron stars has been found, although the parameter space of possible dark matter models is vast, and we've only explored a small fraction of it. The question of whether neutron stars can have multiple stable configurations, or whether there's a unique mass-radius curve, is directly tied to the phase structure of dense matter. Because if there are first-order phase transitions, then you can have situations where multiple equilibrium configurations exist for the same mass, leading to twin stars or even triplet stars with different radii. and these configurations could potentially be metastable, meaning they're locally stable, but not in the absolute ground state. And if so, then there might be processes that trigger transitions between configurations, like accretion events, or mergers that dump energy and matter onto the star and cause it to jump from one branch to another. But detecting twin stars requires measuring masses and radii with exquisite precision for a large sample of neutron stars, so you can see whether the mass-radius relation shows the kind of behavior that would indicate multiple branches. And current observations are tantalizing but not yet conclusive, with some studies suggesting possible evidence for distinct populations, while others find that a single smooth equation of state can fit all the data. So this remains an active area of investigation that will likely be resolved in the next decade as more nicer observations and gravitational wave detections accumulate. The ultimate question that underlies all the specific uncertainties is whether our current theoretical framework is even adequate to describe neutron star cores, or whether there's some fundamentally new physics at work that we haven't discovered yet, because it's possible that the extreme densities and pressures reached in these objects push us beyond the regime where quantum chromodynamics, as we currently understand it, is the complete story. And there could be additional interactions, or new particles, or modifications to our understanding of space and time at small scales that only become apparent under such extreme conditions. And while this might sound speculative, it's worth remembering that every major breakthrough in physics has come from pushing our theories to their limits and finding places where they break down or need to be extended. And neutron stars represent one of the most extreme tests of fundamental physics available anywhere in the universe. So it would be surprising if they didn't teach us something genuinely new about how nature works at the deepest level. And the fact that we still can't definitively answer the question of what's in their cores after decades of study is both humbling and exciting, because it means there's still profound mysteries waiting to be solved and discoveries waiting to be made. At first glance, it might seem like understanding what's inside neutron star cores is purely an academic exercise, interesting only to astrophysicists and nuclear physicists who spend their careers thinking about exotic states of matter in distant corners of the universe. But the reality is that neutron star research connects to an astonishing range of practical and fundamental questions that affect everything from our understanding of the universe's history to technologies that might not exist for decades, but will depend on insights we're gathering right now from these extreme objects. The most immediate connection is to nuclear physics here on Earth, because the same forces that govern how quarks bind together into protons and neutrons, and how nucleons interact with each other in atomic nuclei, are pushed to their absolute limits inside neutron stars. And by studying what happens when you compress nuclear matter to densities far beyond what we can create in laboratories, we're essentially testing whether our theories of the strong nuclear force are correct in regimes we can't access any other way. And if we find discrepancies between what neutron star observations tell us and what our nuclear models predict, then it means we're missing something fundamental about how the force works, which would require revising our understanding of nuclear structure and potentially affect everything from how we model nuclear reactions in stars to how we design nuclear reactors and understand radioactive decay, superfluidity, and superconductivity, which are quantum phenomena where matter flows without resistance or conducts electricity without energy loss, were first predicted theoretically and then confirmed in terrestrial laboratories using liquid helium and specially prepared materials. But neutron stars are natural laboratories where superfluidity occurs on a massive scale, with neutrons forming Cooper pairs throughout cubic kilometers of core material, and superconducting protons carrying currents that generate magnetic fields trillions of times stronger than Earth's. And studying these effects in neutron stars helps us understand the fundamental physics of pairing and quantum correlations in ways that could eventually lead to practical applications like room temperature superconductors or more efficient quantum computers. because the mechanisms that allow particles to pair up and move coherently in neutron star cores might teach us new ways to engineer similar states in materials we can actually work with in laboratories. The discovery of gravitational waves from neutron star mergers has already had profound implications for fundamental physics because it allowed us to test whether gravitational waves really do travel at the speed of light, as general relativity predicts. And the fact that the gravitational wave signal from GW 170817 arrived within 2 seconds of the gamma ray burst from the same event after traveling for 130 million years across space means that the speed of gravitational waves and the speed of light are equal to better than 1 part in 10 to the power of 15, which is one of the most precise tests of relativity ever performed, and immediately ruled out entire classes of modified gravity theories that predicted different propagation speeds, and future detections of neutron star mergers with even better timing will allow us to place even tighter constraints on alternative theories of gravity, and to look for tiny deviations that might signal new physics beyond Einstein's equations. The synthesis of heavy elements is directly connected to neutron star physics, because observations of the Kilonova from the 2017 merger confirmed that gold, platinum, uranium, and other elements heavier than iron are created in the neutron-rich environment of colliding neutron stars through rapid neutron capture nucleosynthesis. And this solved a decades-old mystery about where these elements come from, since ordinary stellar nucleosynthesis in the cores of normal stars can only produce elements up to iron with heavier elements, requiring a different mechanism. And now we know that much of the gold in jewelry, and the platinum in catalytic converters, and the uranium in nuclear fuel all originated in neutron star mergers billions of years ago, which is a beautiful example of how the most extreme astrophysical events are directly connected to the everyday materials we encounter on Earth. And understanding the details of our process nucleosynthesis requires knowing what happens in the cores of neutron stars, because the composition of the dejecta depends on how much neutron-rich matter gets thrown out during the merger, which in turn depends on the equation of state and the tidal deformability. Gravitational wave astronomy is rapidly becoming a new tool for doing fundamental physics that would be impossible any other way, because gravitational waves carry information about space-time itself rather than just about electromagnetic radiation or particles. And neutron star mergers are particularly valuable sources because they involve strong gravity, where the curvature of space-time is enormous and general relativistic effects are large, allowing us to test predictions about how gravity behaves in extreme conditions. And as the network of gravitational wave detectors expands with new facilities like Kagra in Japan, and the planned Einstein telescope in Europe, and Cosmic Explorer in the United States, we'll be able to detect thousands of neutron star mergers per year instead of just a handful. And this flood of data will enable statistical studies that can detect tiny systematic effects that would be impossible to see in individual events, like whether there are correlations between neutron star properties and their formation environments, or whether there are unexpected populations of very massive or very small neutron stars that challenge our understanding of stellar evolution. The connection to the early universe is profound, because if quark matter really exists in neutron star cores, then we're literally observing the same state of matter that filled the entire cosmos in the first microseconds after the Big Bang, preserved by gravity inside these stellar remnants. And this means neutron stars are giving us a window into conditions that cosmologists can only infer indirectly from things like the cosmic microwave background radiation, or the abundance of light elements from Big Bang nucleosynthesis. And studying quark matter in neutron stars could help us understand how the quark-hadron phase transition proceeded in the early universe. whether it was a first-order transition with bubble nucleation or a smooth crossover. And this in turn affects things like the generation of primordial gravitational waves and the formation of the first structures in the universe. So neutron star observations are actually constraining cosmological models, even though the objects themselves are much smaller than galaxies or galaxy clusters. The technology development driven by neutron star research has applications that go far beyond astrophysics, because building instruments sensitive enough to detect gravitational waves, or measure X-ray pulses with nanosecond timing, or process the enormous data volumes from gravitational wave detectors requires pushing the boundaries of engineering and computation. And the same technologies developed for these purposes often find applications in completely unrelated fields, like how the data analysis techniques used to extract gravitational wave signals from noisy detector data are now being applied to medical imaging and financial modeling, or how the precision timing systems developed for pulsar observations are used in GPS and telecommunications networks, or how the machine learning algorithms trained to identify neutron star merger events in gravitational wave data are being adapted for pattern recognition in everything from autonomous vehicles to cybersecurity. The study of magnetic fields and magnetars, which have field strengths around 10 to the power of 15 Gauss, provides insight into how matter behaves in magnetic fields that are so strong they warp quantum vacuum itself, because at these field strengths, the energy density in the magnetic field becomes comparable to the rest mass energy of particles, and quantum electrodynamics predicts exotic effects like vacuum birefringence, where empty space itself becomes polarized and affects how light propagates. And these effects have been observed in laboratory experiments, but magnetars provide a natural environment where they operate continuously and at much larger scales. And understanding how these super strong fields are generated and how they evolve over time requires solving magneto-hydrodynamics equations in the relativistic regime, which is a notoriously difficult problem that pushes the limits of computational physics and requires developing new numerical methods that could be applied to other problems involving plasma physics or fluid dynamics in extreme conditions. The search for continuous gravitational waves from rotating neutron stars is developing techniques that could eventually be used to detect much weaker signals from other sources, because the analysis methods involve searching for persistent sinusoidal signals buried in noise over months or years of data. And the computational algorithms developed for this purpose are some of the most sophisticated signal processing tools ever created, involving things like hierarchical searches, where you start with coarse parameter spaces and progressively refine them, and coherent integration of data over long-time baselines, accounting for Doppler shifts from Earth's motion and timing glitches from the pulsar itself. And these techniques are now being adapted for other applications, like detecting exoplanets through radial velocity measurements, or identifying periodic signals in climate data, or monitoring structural health of buildings and bridges by looking for characteristic vibration modes that might indicate damage. Neutron stars also provide a unique testing ground for quantum field theory in curved spacetime, because the gravitational field near a neutron star surface is strong enough that spacetime curvature is significant, but the object isn't a black hole, so you can actually observe what's happening rather than having everything hidden behind an event horizon. And this allows physicists to test predictions about how quantum fields behave in curved backgrounds, whether vacuum polarization effects are accurately calculated, whether Hawking radiation might have analogs in neutron star magnetospheres, and whether there are modifications to particle physics at high energies that only become apparent in strong gravitational fields. And these tests are complementary to what can be done in particle accelerators, because they probe different energy scales and different combinations of gravitational and quantum effects. The possibility of strange quark matter being the true ground state of QCD has implications that extend to the stability of ordinary matter, because if strange quark matter is more stable, then in principle, all the nuclei around us are metastable and could convert to strange quark matter if they came into contact with a seed, although the conversion rate and the energy barrier involved are highly uncertain, and most calculations suggest the barrier is so high that conversion wouldn't happen on timescales shorter than the age of the universe. But the very fact that we need to consider this possibility shows how neutron star research forces us to think about fundamental questions like whether the matter we're made of is really in its lowest energy state, or whether we're living in a false vacuum that hasn't decayed yet. And while the practical implications might seem abstract, the theoretical implications are profound for our understanding of stability and symmetry breaking in quantum field theory. The study of pulsar timing and its incredible precision, where we can measure rotation periods to 15 or 16 significant figures, has led to the development of pulsar timing arrays, which are networks of precisely monitored millisecond pulsars distributed across the sky that collectively act as a galaxy-scale gravitational wave detector, sensitive to ultra-low frequency gravitational waves with periods of years to decades. And these long-period waves could come from supermassive black hole binaries at the centers of distant galaxies, or from cosmic strings left over from the early universe, or from other exotic sources.
Wow.
And the recent evidence for a gravitational wave background, detected by multiple pulsar timing array collaborations, represents the first observation of gravitational waves in this frequency band and opens up an entirely new window on the universe that complements the higher frequency observations made by LIGO and Virgo. And the techniques developed for pulsar timing arrays are now being explored for applications in precise navigation and timekeeping that could eventually replace GPS satellites with a system based on natural cosmic clocks that can't be jammed or spoofed. The interdisciplinary nature of neutron star research means that advances in this field require bringing together expertise from general relativity, quantum field theory, nuclear physics, plasma physics, computational science, observational astronomy, and data analysis. And this kind of cross-disciplinary collaboration fosters innovation because techniques and ideas from one field often spark breakthroughs in another. And many of the most important advances in science have come from exactly this kind of boundary-crossing work, where physicists, trained in different traditions, come together to tackle problems that don't fit neatly into traditional categories. And neutron star research is a perfect example of this, because understanding these objects requires integrating knowledge from scales ranging from the subnuclear realm of quarks, measured in femtometers, to the cosmic scale of gravitational waves, propagating across megaparsecs, a span of more than 30 orders of magnitude in distance. The educational value of neutron star research is significant because these objects capture the imagination in a way that few other scientific topics do, combining extreme conditions that sound like science fiction with real observations that can be made with actual telescopes and detectors. And this makes neutron stars a perfect vehicle for teaching physics at all levels, from introductory courses, where students learn about gravity and density by calculating how much a teaspoon of neutron star material would weigh, to advanced graduate courses, where students work through the Tolman-Oppenheimer-Volkoff equations and calculate mass-radius curves for different equations of state. And the field attracts talented young researchers who might otherwise go into other areas, because the combination of fundamental physics questions and cutting-edge observational techniques creates opportunities for making significant contributions, even early in one's career. The long-term vision for neutron star research includes not just better observations with more sensitive instruments, but also the possibility of using neutron stars as tools for probing physics that we haven't even thought of yet. Because history shows that whenever we develop new observational capabilities, we discover unexpected phenomena that nobody predicted, like how pulsars themselves were discovered accidentally in 1967 by Jocelyn Bell, when she noticed peculiar regular signals in radio telescope data, or how the accelerating expansion of the universe was discovered through supernova observations that were originally intended to measure the deceleration. And as we continue to improve our gravitational wave detectors and X-ray telescopes and radio arrays, we should expect similar surprises that will force us to revise our understanding of neutron stars and potentially reveal new physics that we haven't imagined yet. And this possibility of discovery is ultimately why neutron star research matters, beyond just understanding these specific objects, because the drive to explain extreme phenomena has always been one of the most powerful engines of scientific progress, pushing us to develop better theories and better technologies that end up having applications far beyond their original purpose.